for this class, I only set out minimal possible goals, which is first to cover the necessary prerequisites, which unfortunately are quite extensive and substantially more difficult than your typical prerequisites for sort of, if you ever encountered, say, topological quantum field theory, typically has way fewer prerequisites. The sort of then the next thing to do would be to explain the statement of the GCH geometric cobordism hypothesis and compute some examples. And today, in fact, I will briefly, maybe not so briefly, even mention at least one example of a type of examples that we are going to compute, which will be a non-topological field theory. In our case, it will be quantum mechanics, which is the simplest possible example in this context. Yeah, but at least the next several weeks will be devoted just to the prerequisites, because I really want to cover prerequisites carefully, just to make sure everybody can follow and not like impose the super high background knowledge requirements. And let's see. I guess some of you mentioned a potential desire to write up, perhaps write up some lectures. So here I listed some optional activities that you may be interested in. Let me emphasize that optional means optional, so you don't have to do anything. You're totally welcome to just attend lectures and do nothing else. But just in case you are interested in perhaps potentially producing a book with your name on it, let me know. I think some of you already expressed a desire to do this, but I'm not sure how if that actually is still true. So let me know if you want to write up a few lectures, and if we have enough volunteers, and that's a big if. Oh, let me pick up a better pen. And that's a big if. We get a book. Let me tell you, in principle, there are examples of successful books. For example, there is a let me just give you mention just one example of what. Let's see. How is this supposed to work? Where is the? Yeah, just as an example, there's a book called Differential Cohomology. Thing by Amabel Gebray and Haig, which could serve as a potential example of what we could produce from these lectures if there are enough volunteers. And that's usually a big if, because often you may have volunteers at the beginning of the lecture, but sometimes the enthusiasm fizzles out, and like you don't have enough volunteers left to continue. Okay, so but just in case you do want to write up, let me know, and I can arrange maybe some coordinated repository for us, and um, we'll see what we can do about this. And I think we now have 2 people recording, so perhaps we can create some archive of video recordings. And I'm not sure what would be the most convenient option for you, but perhaps we can maybe create a semi-private website, or perhaps some kind of semi-private YouTube channel, or anything that will serve as an archive of videos. So again, let me know what would be the most convenient option. All right. Any questions maybe about the organizational part? All right, let me move on. And yeah, please ask questions if you have any. So let me just emphasize that these lectures were meant to be more of a dialogue. When it may not, since I've worked on so long on this topic, it may not be immediately obvious to me what would be sort of the confusing parts for you. So it's you are welcome to ask questions in chat, or in using voice, or whatever other option you can think of. Please ask questions. All right. And how do I?
I have one question. What is the better choice for you? Ask question during the lecture or ask question after the lecture?
No, during the lecture, of course. Yes.
Okay.
Yeah. In fact, it's better if you ask it right away, and this way we can maybe. In principle, we don't have such a severe restriction on time, so there is no possibility of us like running out of time, because we can always continue next time. So I would rather have you guys ask more questions and have more discussions, and maybe we will go more slowly than for me sort of to rush somewhere and without you maintaining an understanding of what's going on. So please ask as many questions as you can. All questions are strongly encouraged and welcome. Yeah. All right. So let me. So in this lecture, at least I wanted to do at least some overview of what this class is about, and why we want to do the things the way we want to do them. So generally speaking, our goal would be to formalize at least some mathematical aspects of quantum field theory. And traditionally, at least from the time of quantum mechanics, there are 2 different pictures of quantum mechanics and quantum field theory. The Heisenberg picture, which emphasizes observables, and the Schrödinger picture, which emphasizes states. And in principle, in the last century, we had a lot of working done on both of those pictures. So the in the Heisenberg picture, you have formalisms such as algebraic quantum field theory, and more recently also factorization algebras of Costello and William. And these formalisms tend to be mostly about doing perturbative complications, meaning you perturb a free field theory, and we'll see what that means, by some infinitesimal action, and you try to see what is happening to your quantum field theory. And then there's also the Schrödinger picture, which is meant to be non-perturbative, or at least be capable of encoding non-perturbative phenomena. It was proposed, I guess, by Siegel and Wicking somewhere in the mid-80s. In fact, at least if I can here recount a story by Siegel. So as Siegel told me himself, somewhere in mid-80s, Ed Wicking was explaining the properties that the path integral construction must satisfy in quantum field theory. And at that point, Siegel, who was in the audience, asked whether the properties or axioms that we are reading on board were just expressing a symmetric monoidal functor from a category of Bordisms to the category of Hilbert spaces. And apparently the reaction of the audience, which was mostly physicists, was not very welcoming, or perhaps they found it very funny, because Siegel just translated something that everybody was familiar with, such as the path integral, into some weird categorical nonsense. But that's how our subject was born, and of course Siegel first formalized CFT, conformal field theory, which in its turn encouraged a whole range of developments for topological quantum field theory, the case where your Bordisms don't have any geometric structure, such as a conformal structure, but only have perhaps an orientation, or maybe some similar topological structure like spin or spin C or whatever, but no geometric structures like Riemannian metrics or conformal structures or anything of that type. And the primary reason for this sort of switch was that it is extremely difficult to construct examples or prove existence of any non-trivial Functorial field theory in dimension 2 or higher. And we'll see more reasons for this a bit later in the class. But essentially, the only examples that we had for non-topological Functorial field theories, at least so far before the geometric cobordism hypothesis, were just 2 or 3 examples in dimension 2, and even these examples were not extended. So I will explain what extended means in a second, but it's a property that enables the geometric cobordism hypothesis to work. So there was essentially in dimension higher than 2, as far as I'm aware, there were simply no examples at all. And that was maybe perhaps one of the reasons why the formalism didn't receive more attention than it should have, because with so few examples, it's difficult to work in the area. this is not to say that, of course, a lot of interesting work has been done, especially, well, and overwhelmingly actually on CFT, conformal field theory. But still, up until now, there were very few examples. And perhaps one of the points of this class is to explain how you can compute examples in a much more easy fashion than before. All right.
As I understand, Heisenberg and Schrödinger pictures are equivalent to each other, yes, in some cases, or
Yeah,
it
in
is not
principle,
so.
yeah, I mean, in principle, there are some connections you can establish between these two pictures. In fact, the factorization algebra picture seems to be reasonably well connected. In principle, we know some constructions. For example, we know a construction of a functorial field theory from a factorization algebra. And I think I do know how to generalize it to geometric structures, non-topological geometric structures, meaning, for example, Riemannian metrics and whatever. So it is possible to define factorization algebras on manifolds with geometric structures, such as Riemannian metrics and whatever. And in principle, I think we have a reasonable idea how to construct a functorial field theory from a geometric factorization algebra, for example. So yes, absolutely. There are certainly connections you can establish between these two pictures, including some reasonably some constructions that in principle we do know what to do. In that case, the only question is having enough people to write this all up. So far, there are only two of us, meaning me and my co-author, who are proficient in this formalism. So perhaps one of the goals of this class would be to enable you guys to do your own projects in this area.
Establishing
Yeah.
equivalence between these pictures, yes, in some cases.
I wouldn't go as far as to claim a complete equivalence, or at least I cannot give you a statement that would be an equivalence right away, but in principle, we can discuss like it may not be impossible, but I would just be hesitant to claim it right away because I don't think I have a precise statement at this point. We certainly do have constructions that allow you to pass from one picture to another, from Heisenberg to Schrödinger, and conversely, in principle, we do know some constructions that allow you to go both ways. But a complete equivalence, I would not claim yet at this point.
Do you
Yeah.
consider conformal nets as geometric factorization algebras, or are they inherently very topological in nature?
Yeah. Conformal nets would be present on the factorization algebra side, for example.
No, but would you consider them to be geometric factorization algebras in whatever way you define them?
It depends, I guess, on what conformal net you're talking about, but yeah, I guess in principle it's fine to consider them as geometric in a sense that they do depend on the interval, like the yeah, I think there is a non-trivial smooth, at least, well, we can certainly say there's a non-trivial smooth dependence on the interval. So when you have a conformal net, if your interval will rotate smoothly, in principle, you can make precise the statement that the image of the corresponding algebra inside the algebra associated with a bigger interval varies smoothly. So changing an inclusion of intervals smoothly should change the inclusion of algebra smoothly.
But this
So
is
in
not
that sense,
this is not some written down somewhere. Like people don't define
yeah,
like the.
that's yeah, I don't think that's actually written down. So
Mhm.
it's again, but from the constructions, it seems like it should be true. So I guess what I'm saying here is like I don't really have a written proof that they are conforming as our geometric factorization algebras, but perhaps this is something we should expect to be true, and perhaps we should consider it to be a reasonable conjecture.
Thank you.
Okay, more questions? All right. Let's see. All right, so the formalism, yeah, so I somehow here the pen is not so good, but I hope you can still see what's written here. The formalism of functorial field theory, maybe I should say, it encodes both the data of a classical field theory, or perhaps a bit more accurately, pre-quantum field theory, which is classical field theory plus potentially additional input data coming from constructions such as a Dirac charge quantization and the like, where, for example, instead of saying that an electromagnetic field on a Lorentzian manifold is a differential true form, you can say it is a principal U1 bundle with connection, which is a slightly more refined description, which allows you to, for example, to account for the Aharonov-Bohm effect and similar effects observed in physics in practice. We'll talk a bit more about this later. And it also allows you to encode, of course, the quantized field theory, which is why you call it a quantum field theory. But perhaps that's the reason why I prefer the name functorial field theory and not functorial quantum field theory, because the formalism encodes both classical and quantum field theories. So in the generic case, you probably just want to say functorial field theory. And I should probably also mention the terminology functorial quantum field theory is due to Urs Schreiber, who I think had a similar motivation to remove the word quantum from the description, because you can also include classical field theories. And I think at some point, yeah, I think, well, at least people working on the Stoß-Geithner program, for example, immediately adopted this terminology. So today, I think we all talk about functorial field theory, and I think there's increasing awareness of this terminology. But the terminology itself is maybe about, I would say, maybe 12 years old. So it was actually introduced fairly recently. So let me just give you a single example of what we discussed so far, and this will be just a particle propagating in a Riemannian manifold. And I want to explain to you what a classical field theory is in this case and what a quantum theory is in this case. And of course, at this point, I don't necessarily have to omit many details. In particular, in this description, I will omit everything connected to, say, supergeometry or aspects related to homotopy theory and higher category theory. So for those of you who are maybe have more familiarity with the matter at hand, you will see that perhaps a lot of details are omitted. And of course, that's not the point. The point is maybe to communicate some general ideas and to give you a very rough idea what we might be doing when we try to construct concrete examples, which will be a month or two from now at least. Okay, so as I said, we want to consider the example of a field theory encoding a particle propagating in a Riemannian manifold. So our input data will be a Riemannian manifold X, which you think of maybe perhaps as a some kind of a space where the particle can propagate, like perhaps even a three-dimensional space or whatever. And you also need a well, at least I'm trying to make the things at least slightly realistic. So let me say we have a finite dimensional vector bundle, and this vector bundle is equipped with an action of the Clifford algebra of the tangent bundle. If you don't know, so that's by the way known as a Springer bundle. If you don't know what a Clifford algebra is, please ignore this aspect. It's not truly essential. It just gives you some rough idea what you can expect. Okay, and given this input data, let me first let's see. Well, given this input data, let me first explain how the classical, or more precisely pre-quantum field theory works. So a pre-quantum Functorial field theory will be a symmetric monodical functor between two symmetric monodical categories. And by the way, if you don't know what a symmetric monodical category is, we are also going to explain this in the 2 lectures from now, I guess. So if you don't know what a symmetric monodical is, for example, please feel free to ignore it and just think of a functor. Okay, so what are the categories involved here? So the source category is known as a category of Bordisms. And so I call it the category of one-dimensional. This is one here. One-dimensional category of Bordisms equipped with a Riemannian metric. So that's what Riem refers to here. And a smooth map to X. That's what this times X mean here. So let me describe to you objects and morphisms in this category. Objects will be, well, in the first approximation, there will be just points in X. So you have a point.
Please about superscript in category of Bordism. It means that we have Riemann metric on each, just this.
I mean, yeah, so this is an example. It's called a sigma model, and of course you can make it supersymmetric. In fact, here, strictly speaking, to encode everything properly, perhaps we should throw in a single odd dimension. But again, I'm not going to talk about any super geometry right now, or any of the more advanced aspects. Right now, we are just trying to encode the typical possible example, which is quantum mechanics. Did I say it was quantum mechanics, by the way? Yeah, well, let me write here, quantum mechanics.
Reynolds superscript is just a denotation, yes?
Sorry, say again?
subscript, superscript is just a denotation. Yes.
So can't quite hear you. Could you make your a bit louder, please? Yeah.
The superscript is just a designation. Yes. In category of forgiving.
Well, right now we are not talking about superstrings yet, so it's simply not like later when we define a two-dimensional category of Bordisms. If you want, a string will be an object, which will be like a bunch of circles, for example, or a bunch of intervals if you do like open or closed strings, and morphisms will be two-dimensional Bordisms. But right now we are just doing a more elementary example. Yeah. Yeah. So yeah, but you're maybe correct to point out that, of course, the original motivation for the formalism was not to encode a quantum mechanics, but it was to encode some aspects at least of superstring theory or string theory in general. And of course, the original Bordism category was two-dimensional. But for this example, we are just doing one-dimensional field theory, which will be encoding quantum mechanics, not superstring theory. All right, so
Why would you call this a pre-quantum? Like, why are we doing this as an example of a pre-quantum?
yeah, pre-quantum because well, we haven't quantized it yet, so the operation of quantization will be in fact will be explained in maybe 2 or 3 minutes from now. And that will be basically amount to extracting the Dirac operator. But in this picture, we don't have any, everything is finite dimensional. And you will see in a moment how we encode essentially what is a classical action using this formalism. So only the classical action will be encoded for this first example. And the quantization will be done later. So that's the point, yeah.
I somehow was of the opinion that if we are landing in Hilb or Vect or N-Hilb and Vect, then by default we are a QFT. And if we are landing in something like Lagrangian correspondences or something else, which is still not a vector space and linear maps, then we are doing something pre-quantum. But this probably is not the terminology that you're using.
Yeah, no, of course, I mean, yeah, so if you want to take a pre-quantum theory in your sense, like Lagrangian correspondences, and take functions, so send a correspondence to the induced map on functions, and this will be a pre-quantum theory in this sense. So
Yes,
in
exactly.
principle, the two pictures are very, very closely related. They're not really that far apart.
Okay, sure. Thank you.
You're welcome. All right, so yeah, so I think so an object will be a point mapping into X, but in principle, like, and maybe we shouldn't bother too much with these details at this point, but to ensure that we can compose Bordisms, I also want a little one-dimensional germ of this point, meaning I actually have a one-dimensional manifold containing this point, and I'm interested in arbitrarily small open neighborhoods of this point. And this germ, this one-dimensional germ, is equipped with a Riemannian metric, meaning I can measure distances inside of here. And more generally, we also allow an arbitrary finite collection of such points as an object. So take several points. Each point maps to some point in X. In general, these will be different points. And this is your object in your category. Morphisms in this category are called Bordisms. That's how I can change colors. Nice. And what is a Bordism? Well, here's a picture. So these 3 points on the left, that will be your source. And this point on the right is your target. Or if you prefer categorical terminology, domain and codomain. And in between, you have some one-dimensional manifolds that basically contain these points as boundary points. And of course, here it's not quite the boundary, but rather it's the boundary with some color. Yeah, the other terminology, sometimes this is called a color. And well, germs, colors, is the same thing. And this one-dimensional Bordism is equipped with a Riemannian metric. And of course, for a one-dimensional manifold, specifying a Riemannian metric on a one-dimensional manifold basically amounts to specifying its length. And that's what I indicated here when I said length. So this interval, for example, has a length. This circle also has a length. And this interval here also has a length. But of course, when you go to higher dimensions, you will see much more interesting geometric structures. Like Riemannian metrics in dimension 2 are already much more complicated. And this Bordism is also equipped with a smooth map to X. So really, a Bordism is just basically some kind of a collection of paths in X. Now, Bordisms can be composed by sort of gluing 2 pictures together. So here you can see, for example, 2 Bordisms being composed, being glued together in a single Bordism. So you take the common boundary, and it is precisely at this point that you make use of the germs of points, which allows you to, well, generally speaking, if you imagine, for example, you have one pass, one smooth pass, and another smooth pass. The gluing need not be a smooth pass, right? So here the gluing has a derivative which has a discontinuity at this point. But if you require that some germ of a pass has to match the germ of the next pass, then the gluing will be smooth. And that's precisely why I insisted here that we take germs, which ensures that the gluing is a smooth manifold. So that's a sort of a point you typically see only in non-topological field theories, because if you just have a smooth manifold without any additional structure, then in fact the theorem of Milnor tells you it is always possible to glue such smooth manifolds together in an essentially unique way, meaning the space of such gluings is a contractible space. And in some very, very special situations, like, for example, conformal structures also possess a similar result, known as the conformal welding theorem, which also allows you to glue bordisms together in an essentially unique way. But generally speaking, that's simply not true. For example, if you have a geometric structure given by a smooth map to a manifold X, then it's simply not possible to glue bordisms so that the gluing is a smooth manifold. And it is precisely for this reason we always insist on having all objects equipped with a collar, with a little collar or a germ of this object, which ensures the gluing is smooth. Okay, so that's how the category is defined, and the symmetric monoidal structure is simply given by a disjoint union. So if you have two objects, you can stick them together, take their disjoint union, and this will be a new object which combines together the previous two objects. All right. Any questions about the bordism category?
As I understand, in one dimension, we have just this morphisms, yes, line and circles. Yes, it is possibly
Exactly.
some
So,
kind of theorem of classifying, yes?
yeah, of course, in dimension one, there's a complete classification of one-dimensional manifolds. One-dimensional manifolds without boundary are precisely intervals, or real lines if you want, and circles. And that's exactly what you see in this picture. You see at least one circle right here. And all the other bordisms are or another circle here, yes. And all the other bordisms are intervals. The only point, of course, is that if you have an interval, in principle, you can assign its endpoints to the domain or to the codomain. And that means you are going to have not one interval, but in principle, three different intervals. So this is called the left elbow. This is called the right elbow. And well, this one is just called an interval. And of course, that's just a topological classification. You still have geometric structures on your intervals or elbows. So that's still present. Yeah, but of course, in principle, there are analogs of such constructions in higher dimensions where we will talk about handles. But of course, the real nice classification only exists in dimension 1 and 2. In dimension 2, in principle, you can still classify surfaces by their genus and possibly the number of boundary components. But in dimension 3 and higher, that's hopeless. So, and we definitely want to be able to work with dimension 3 and higher. So whatever tools we'll develop will enable us to do this without doing any type of classification of manifolds. Yeah. All right. Let me advance. So recall that we are so here on the left, you see we are trying to construct a symmetric monoidal functor from a second category of bordisms. like we just discussed, to the target category, which in our case will have a very simple description. It's the symmetric monoidal category of vector spaces. Its objects are vector spaces, its morphisms are linear maps, and the monoidal structure is simply the tensor product. Given two vector spaces, you can take their tensor product, and given two linear maps of vector spaces, you can take their tensor product of linear maps. So that's a very simple category. And you may notice, like at this point, I would rather not talk about topological structures on these vector spaces. For example, I'm not going to talk about Hilbert spaces at this point, and I will not try to explain how we topologize or how we ensure that these linear maps, for example, depend smoothly on the lengths of the interval. All of this can be addressed, but perhaps we shouldn't bother ourselves with such details right now. All right, so next construction to describe is the actual functor from the category of Bordisms to the category of vector spaces. And the very first thing I should explain is what to do to, giving an object in this category, which, as you may recall, let's see, we defined as a point mapping to X together with some one-dimensional germ. And in our case, the construction is really simple. You have a point in X, and to this point, I'm going to assign a vector space. And what is this vector space? It's precisely the fiber. So if you may recall, we had this input data, which was a spinor bundle, a finite dimensional vector bundle with an action of the Clifford algebra. And let me not tell you the full definition here. It's not terribly important right now, but if you know it, that's fine. If you don't know it, that's also fine. But the main point here is like a vector bundle over X. If you pick a point in X, you can extract its fiber over this point, and this will be the value of your, let me actually give a name, because this functor I call it P. So P applied to this object will be the fiber of the spinor bundle over the point P. And if you have a collection, a finite collection of points as an object, such as, for example,
big P means functor, yes? And small p is a point.
Capital P denotes a functor, yes. And this is a small p, so it's different, yeah.
SP is a fiber, yes?
Yes,
SP.
that's right, yeah. SP with a subscript P denotes a fiber. Maybe I should, oops. Why can I not? Oh, I see. I chose the wrong type of eraser. Maybe I should say free eraser. Yeah, I don't know how to denote a small p, but maybe that qualifies as a small p. I don't know. Yeah. All right, yeah. And a finite collection of points is mapped to the tensor product. And what this should remind you of, eventually, of course, this will remind you of the fact that in quantum mechanics, the space of the vector space of states of two systems, two independent quantum systems combined together will be their tensor product, the tensor product of the two vector spaces of states of individual systems. But at this point, we are not encoding quantum mechanics yet, and you really should think of those vector spaces not as vector spaces of states, but rather vector spaces encoding perhaps something like the internal degree of freedom of your particle. Like, for example, here it's a spinor bundle, it's fibers, there will be some elements in a finite dimensional vector space of spinors, which is finite dimensional and encodes maybe finitely many, like a finite degree of freedom encoded by the spin in quantum mechanics. But eventually, of course, this will translate into the general principle in quantum mechanics that vector spaces of states transfer together when you combine two independent systems. All right, so and finally, I should tell you what happens to morphisms. Here is an example of a morphism, and it's an interval. An interval is like maps to x, by the way. So there is a map to x. So this is really, you should think of it as an interval, a pass in x from one point P to another point Q. And to this pass, I assign the parallel transport map. So I'm not sure. Again, if you're not familiar with parallel transport, I will try to explain it later in the next lectures. But for now, the pictures you should be imagining is that you have, here's your x. Here is maybe some vector bundle over x. So over each point, I have a vector space. So this is a vector space. So each point has a vector space over it. So if this is, for example, point P, then this is SP. And the parallel transport allows you to sort of, you can start at any point in any fiber. And the parallel transport tells you how to transport this point to other fibers. So what it gives you is for any pass in X, like here I have a pass from one point, let's say from point P to a point Q, and let's say I transport from right to left, like here. And this gives me a linear map from SP to SQ, a linear map between the corresponding fibers. And that's precisely the value of your classical or pre-quantum field theory on a pass. And of course, you may also be wondering what happens to all the other Bordisms, like, for example, let's see. What happens to the right elbow, left elbow? And the answer here is very simple. If you know what happens to an interval will be a linear map. Let's see, how should I? Yeah, so to an interval, you assign a linear map like this. And imagine now if I bang one of the endpoints to the left, so I get, say, the right elbow here. Let me also draw the endpoints for your convenience. Well, what does this type of bending operation correspond to in terms of linear algebra here? Well, that's very familiar. Like if you have a map, let me use a green color. If you have a linear map of vector spaces from V to W, say, then sort of bending this map amounts to moving one of the vector spaces to the other side and taking its dual. So such a map F induces a adjoint map from V tensor W dual to the base field. In our case, let's say as complex numbers. And of course, here I'm using the W is a finite dimensional vector space. Of course, this wouldn't work in general for infinite dimensional vector spaces. And of course, you can also move it to the other side and get a map from C to V dual tensor W. And that's what happens to all the other left elbows, right elbows. They also receive, so to say, the corresponding parallel transport map, but appropriately modified in accordance with this recipe here. All right. Any questions about the pre-quantum field theory before I move on to explaining the quantum field theory?
Yeah, is there a canonical choice of connection on the spinor bundle?
Yes. So, well, okay. Yes and no. So if you are working with a real spinor bundle, then there is such a choice. And the reason for that is that, well, what is, so first of all, recall that any Riemannian manifold has a canonical connection on its changing bundle, which is the Lévy-Civita connection. And the Lévy-Civita connection gives you a canonical connection on the frame bundle, the principal ON bundle over your Riemannian manifold X, where N is a dimension of X. So the frame bundle, the orthogonal frame bundle, also acquires a canonical connection. And you can then restrict to the group SON, say by imposing an orientation on your Riemannian manifold. And then the spin group, the ordinary real spin group, is just a twofold covering of the group ON. So SON, sorry. So spin N is a twofold covering of the group SON. So the canonical connection you have constructed on the principal bundle of oriented orthonormal frames gives rise to a completely canonical connection on the twofold covering. And this is precisely the principal bundle encoding the spin structure. So it requires a canonical connection, which is essentially the Lévy-Civita connection. And now, if you take the associated bundle of this principal bundle, which is associated to the spin representation, it induces a canonical connection on the spinor bundle. So for real spin structures, the answer is yes, you require a canonical connection. For spin C structures, so a spin C structure uses the spin C group. So what is a spin C group? It's an extension of the group SON by the group U1. And in this case, of course, you are not going to get a canonical connection on the corresponding spin C bundle, principal spin C bundle, because the corresponding map is no longer a covering map, rather it has fibers of dimension 1. So you have a bit of additional data you need to specify, and that's sometimes called a geometric spin C connection, or perhaps a geometric spin C structure, where sort of to every spin C structure, you have a canonical line bundle associated to it. And if you specify a connection on this line bundle, which is an additional data, then this connection can be combined with the connection with the Levi-Civita connection to construct a connection on the Springer complex Springer bundle. So in the complex case, you need a bit of additional data to get a connection. But in general, yeah, the Levi-Civita connection provides most of the connection, so to say.
I'm sorry.
Yeah.
I don't quite understand. Are you saying that like any orientable manifold admits a spin structure?
No, of course, it's an additional abstraction. It's a topological abstraction that, and that's why I say in our case, the manifold is equipped with some spin structure. So of course, it's certainly possible to construct oriented Riemannian manifolds without a spin structure. And I'm not saying they admit one. I'm just saying one is given to us as an input data. Yeah. All right. More questions?
To understand spin structure, we may count also in the quantum case and also in quantum case, in both cases in general, yes?
Yeah, no, of course this will all of this will find its way in the quantum field theory, yes. Which is in fact the next step in our construction here. Yeah.
Can you say again how this right elbow is given? Like if you evaluate the morphism of the right elbow by means of our quantum field theory, how you evaluate this precisely?
Yeah. So let me, in fact, let's see. Just a second. Let's use this wonderful. Nice. So let me. So you wanted to do the left elbow or the right elbow?
Both is fine. So I don't care which one.
Okay. So here is the right elbow. Yeah, by the way, the way to remember this terminology is it literally refers to your elbows, actually, as in like right elbow and left elbow. Yeah, so you have 2 points, P and Q here. And the parallel transport map gives you, so if you interpret this path as going from P to Q, you have a parallel transport map from SP to SQ. And the right elbow is supposed to be, however, a morphism. Yeah, sorry, I guess at this point I should at least mention orientations. So I should have mentioned, yes, I wanted to omit this detail, but maybe I shouldn't. So let me just say with a Riemannian metric and orientation. So in fact, I also know which, like for example, a point can be, say, oriented this way. And an interval can be oriented this way or the other way. The sort of point of this construction now is that there are, in principle, two orientations possible for a point. Yeah, maybe I should have been a bit more precise with my pictures. So a point is not just a point with a germ, it also knows in which direction you are going to be composing it with bordisms. Meaning, so here I shaded a part of this germ, one half of this germ. This is where the actual bordism will appear. So when I shade, and maybe I should have shaded it here. Let me just a second. So when I shake it like this means an actual bordism will appear here. And so, for example, that means, for example, here, this part is shaded. This part is shaded. This part is shaded. Appear here in the source. And for the target, the convention is reversed, and that means the shaded part will be not in the bordism. So here, this point is a target, and the shaded part is not in the bordism. We can draw similar pictures everywhere. So here, this is shaded, this is shaded, this is shaded. And here is the target, so that's not in the bordism, so we shade it like this. What's the point of all this? The point is when you glue the source to the target, you match the shaded parts. The shaded part is matched to the shaded part, and this ensures that you glue in the correct order, because otherwise there would be a certain ambiguity, right? So here you could have matched this tiny germ to either this part or the other part. And in order to distinguish between these two situations, we need to shade one of the two parts. Okay, so that's maybe one aspect I sort of suppressed in my original description. As you can see, the bordism category is a lot more complicated than it looks on the initial sort of look, and that's why we will be spending a lot of time explaining what it is properly. And independently from this, in addition to this, there's also the data of an orientation. And that means a point can be oriented, an orientation on a one-dimensional manifold is simply a choice of a direction, so to say. And that means, in particular, that a point can be oriented in two completely different ways. This one-dimensional segment can either be oriented this way, or it can be oriented the other way. And these two orientations give you two different objects. And in one of those objects, the orientation points in the shaded direction. And this we call the positive point. And in the other of those cases, the orientation is pointing away from the shaded direction. And this we call the negative point. So refining what I previously mentioned, the positive point gets sent to SP, whereas the negative point, one moment. And what happened now? Okay, I'm not sure what happened now. I want to select this and rescale it, and maybe this one. Oh no, that's bad. Maybe this one. Let's see. Nice. I have now more space to say what happens to the negative point. So here's my negative point. It's oriented in the other direction. It also has a map to X. Let's say Q. And this gets sent to the dual vector space SQ dual. So that's just home from SP to complex numbers.
SQ.
Oh, sorry, SQ, yeah. Thanks. SQ. And now I can finally tell you what happens to the elbow. So here, if you look carefully, you have this elbow. This part is shaded and this part is shaded. And let's pick some orientation for the elbow. It doesn't really matter which one. Let's say our elbow is oriented this way. Now let's look carefully at the 2 points. Now for this point, the orientation points toward the shading. So this point on top, the point P, is a positive point. Next, look at the bottom point. The bottom point, the orientation points away from the shading, so it's a negative point. So that means the kind of linear map we are looking for right now should be a linear map from the value on these 2 points, which will be the tensor product. Oops. My software crashed. Not good. One moment, let me restart it. In principle, a good software, but sometimes it just crashes. I guess I should share my screen again. Okay, can you see it again now?
Yeah.
Oh, thanks. Let me hope now I can rescale this. I'm not even sure what caused this crash. Okay. So what I was saying is like we want a linear map. Okay, that's definitely not sick enough. A linear map from SP tensor SQ dual true. And what should we, so this is a Bordism from 2 points to the empty collection of points. What should we assign to the empty collection of points? We should assign the tensor product of the empty collection of vector spaces. And what is the tensor product of the empty collection of vector spaces is just our base field, so that's complex numbers. So what is this map here from SP tensor SQ dual to complex numbers? I guess I'm out of space again, so let me do the same trick. Okay, I don't feel a gag, but why is it not? I'm not sure why I cannot rescale this. Okay, finally. So how is this map defined? Well, according to the universal property of tensor products, to specify a map out of this tensor product, I have to specify a bilinear map that sends a vector S together with a linear form on SQ. It has to send it to some complex number. Well, what is a complex number? Here I have this parallel transport map. Let me call it as gamma. So gamma is this Bordism here. And what I do is I evaluate f on as gamma applied to S. Maybe I shouldn't have called it S. Let me pick a different letter, maybe V. Yeah, V. Right, so I parallel transport vector V, which is a vector here in SP. I do a parallel transport to SQ, and then I evaluate the given form in SQ on P, on this transported vector. And that's how the map for the right elbow is defined.
Thanks.
Yeah, you're welcome. More questions? All right, let me gently transition into discussing the quantum, how to construct the quantum field theory in the same example. So the quantum field theory will be a will be a functor, a very similar functor. The source category will be also a category of Bordisms, defined exactly the same manner, but now there is no map to X. There is no map to X anymore. So what happened to X? In fact, you will see exactly what happened. So a Bordism now will be a point, and an object will now be a point with a one-dimensional germ, and Bordism will be just a one-dimensional Riemannian manifold without any maps to X. And since we already mentioned that all points are oriented, maybe I should be more precise and actually draw true points for you. One of which will be positively oriented. The other one will be negatively oriented. And these points will send them respectively to the to certain sections of this vector bundle S that we previously considered. And actually, I already wrote it here. So the positive point will map to the smooth sections, I guess, and the negative point will map to the distributional sections. If you arrange things correctly, and that's why I didn't want to talk about Hilbert spaces or topological vector spaces, but in principle, it is possible to arrange things in a way that the dual of smooth sections will be distributional sections, and the dual of distributional sections is smooth sections. And I believe one of those, in physics, I guess you call one of these, and I always forget which one it is, but I think this could be like bra vectors. So these guys could be called bra vectors. And maybe these ones should be called ket. All right. Next, I have to explain to you what happens at least to the interval. So here's an interval of length t. Such an interval we map to the so-called time evolution operator, which is defined as the exponent of t times some constant. In fact, I guess in physics, you would often set the h bar constant just to 1 because it's so convenient. And you times the square of a certain differential operator called the Dirac operator.
As
So
I
these
understand,
called-
they act on one-dimensional smooth manifold in our case, yes?
What acts? Sorry.
Where our operator of evolution acts.
No, here it will act on this vector space, which is the sections of the Springer bundle, and the Springer bundle is a vector bundle on X. So it will be a differential operator on X. X can be a Riemannian manifold of any dimension. Right, so and just in case you're interested, but this is not really essential, but in case you're interested how it is defined, first apply the Springer connection that we previously discussed. This will land you in sections of the co-tangent bundle, and there's a Springer bundle. then you can use the metric to identify the co-Kencing bundle with a Kencing bundle. And finally, at this point is where the Clifford algebra action starts to matter. So the Kencing bundle embeds into the Clifford algebra of the Kencing bundle. And the Clifford algebra will act on the Springer bundle, which moves you back to the Springer bundle. This composition here is called the Dirac operator. And just, I guess as a primitive example, if X is simply the real line, then the Dirac operator is simply, for example, minus I times the derivative with respect to the, times the usual operators that take the derivative of a function on a real line. And I guess in this case, because the Springer bundle will be also a trivial bundle, so it's just as a very simple example, which at least because the Dirac operator is a first order differential operator, so its square will be a second order differential operator. Which differential operator it is? It's the Laplacian operator. And given this Laplacian operator, you can take this exponent, and this will be your time evolution operator. Oh, sorry, I guess I should have mentioned already in the previous section why composition is preserved. Because I defined the composition for you, but I didn't mention that, of course, composition of Bordisms. And yeah, I guess I have just enough space to very quickly indicate if I have a path, one path of from point P to point Q, and another path from Q to R. Well, these paths get assigned to parallel transport maps from SP to SQ, and from SQ to SR. And whereas we can also compose these two Bordisms in a single Bordism from P to R. And the functoriality condition tells you that, okay, this Bordism from P to R gets assigned a map from SP to SR, which is the parallel transport map. And this triangle has to commute, meaning to parallel transport, if you parallel transport along a composition of two paths in X, from P to Q and then from Q to R, this gives you the same result as a parallel transport along the whole path taken at once. In other words, a parallel transport is a functorial operation. And this functoriality finds its way directly into this construction of a functorial field theory. To some extent, you can think of the pre-quantum field theories as some kind of a highly sophisticated and extremely generalized notion of a parallel transport, which is much more general than the usual notion, but to some rough extent, it's fine to think of it as a parallel transport. Okay, so now let me go back to the discussion of the quantum field series. So in the so here we map an interval of length t to this exponent, And of course, you can immediately see right away that composing two intervals, one of length t1 and the other one of length t2, will map to the composition of exponent of t1 times d squared and the exponent of t2 times d squared, which is the exponent of t1 plus t2 times d squared. And because of this property of the exponent, composition is preserved. All right, so that gives you at least a rough idea what the quantum field theory is. Any questions about the quantum field theory before I move on to discussing how to quantize?
As I understand,
Yeah.
we consider t as a path, yes? In physics, it's named time, yes? But there
Yeah,
we
so
consider
here
as a path,
this
yes?
Bordism is it's a one-dimensional oriented Riemannian manifold. So its only invariant is its length. Yes. So yeah, you can think of it as an abstract path, which is not a path in any manifold, but rather a path on its own. Yeah.
It is a path in its own, yes? It is not considered as a path in
Yeah,
any
it's not
manifold.
this interval doesn't map to X. It's just a one-dimensional Riemannian manifold with an orientation, so it has a length, but it has no map to X, right? And you can see X is not present, so to say X migrated to the right side, right? You can see that the sections of S are sections of some vector bundle over X, and D is a differential operator over X. So on the right side, in the category of values, everything now has X in it. Whereas previously, for the pre-quantum field theory, which you can still see on the left, everything was associated only to some specific part of X, like a point in X or a path in X, but not the whole X. So what happened in the quantum field theory, the dependence on X on the Bordism category disappeared, and instead X migrated to the right. All right. Let me now migrate to the last part of this discussion, which is how exactly do we pass from the classical field theory to the quantum. And in principle, there's a classical construction. So the path integral construction. So that's the old way to quantize. It originated in 1949. And this recipe, well, for objects like points, it doesn't really tell you much in this case. It just tells you basically what you do is you evaluate your pre-quantum field theory on all possible objects, in our case, all possible points in X, and you take the product of all these vector spaces. And for details, I have no time to explain right now. We can make this product, which a priori would be just arbitrary discontinuous sections. We can force them to be smooth. So this will be just smooth sections of S. But
Please,
much more interesting.
repeat.
Yeah.
Q is Functorial, yes, from Bogdan to categorical vectors.
Yeah, so
Yes,
Q
yes.
is this
Mhm.
functor that we defined.
Ah.
Oh, yeah. Did I say it's Q?
Okay.
One moment. Maybe I didn't.
I see. Because,
Yes, yeah, this is Q. Yes, this is Q. Maybe I should have. Oops. Yeah, this is our Q. Yes. So the question is, how can we obtain this formula just from the pre-quantum field theory, which is P? And the answer is you do something called the path integral. And again, let me write it very informally, but in principle, this can be made rigorous in the one-dimensional case. So you need to define a linear map from sections of S to sections of S. Let's call it UT, where T is the length of our interval. And to define a linear map, you can define its integral kernel in the sense of Schwartz. And the integral kernel, when you evaluate it on 2 points, x and y, so here x and y are 2 points in capital X, because you are defining the integral kernel of a differential, sorry, of just an operator between two between sections of vector bundles over X. And when you evaluate the integral kernel on some points, X and Y, you can say it's precisely the integral of the value of your classical or pre-quantum theory evaluated on all possible paths in your manifold capital X connecting X to Y. And as we have seen, a path is basically a Bordism. I guess I should have called them P and Q, but it doesn't matter. A Bordism from X to Y. So you evaluate your P on all such Bordism, all possible paths from X to Y of length T. So T is the length of this path. And you integrate over this infinite dimensional space of such paths. So that's not your typical integral. That's something called the integral against a Wiener measure. So here we integrate against the Wiener measure. I don't know, let's call it dw. So this refers to the Wiener measure. You don't have to know what this means. It's fine to think about this informally. So you integrate against this Wiener measure, and this gives you the integral kernel of this operator associated with the interval of length t. So that's how you use the data of a classical or pre-quantum field theory to construct a quantum field theory. So that's a classical recipe, and in principle, you can do similar things in dimensions higher than 1. Like, for example, two-dimensional series, you will be integrating, you will be trying to integrate along all possible maps, but now not from an interval, but from a surface. So a surface maps to X, and you will integrate along all possible maps from such surfaces. And unfortunately, we don't really know how to define this rigorously in any dimension other than 1. So for integrals along all paths, we do know how to do it. And in higher dimensions, there are all sorts of analytical problems, which does place a massive obstacle in against this formalism. Like if you are unable to do this quantization procedure, then what's the point? But of course, I would like to maybe tell you about how the geometric cobordism hypothesis enables you to maybe circumvent this problem, and here's a sort of a teaser for the why GCH or geometric cobordism hypothesis is a useful tool. It allows you to maybe circumvent this problem of defining infinite dimensional path integrals. And I try to sort of briefly explain this construction in this little diagram. So you have a functor, symmetric monoidal functor P from this bordism category to vector spaces. And you have this the other bordism category for the quantum field theory, which is bordisms without a map to X. And you have a functor Q from this bordism category to vect. That's what you want to construct. And there is also a map from one bordism category to another, which is this projection P. Pi, which discards, this projection discards, it takes a bordism and discards the map to X. It throws it away, and it retains, however, the remaining metric. And the idea is that if we have the gate of two such functors, then there is a purely categorical construction called the Kahn extension, which allows you to construct a functor Q given the functors P and pi. And of course, there are many bells and whistles that have to be attached to this in order to make this work, because of course, the usual Kahn extension, this is not a smooth construction, and you have to make it smooth in order to make it work. So part of the what we will be discussing is how to develop the so-called smooth category theory, which allows you to, for example, in the smooth category theory, co-products and products will be replaced by, so in the usual discrete setting, a coproduct or a product of vector spaces is a direct sum or direct product. But in the smooth setting, the coproduct will be a distributional section with compact support, and the product will be a smooth section. So these constructions, like smooth sections and distributions, can be obtained in a purely categorical manner. And I claim also the Dirac operator can be extracted in a similar way. So just to be clear, this describes some ongoing project with Gangrady, which we haven't written up yet. So in principle, details can change, but we are currently working on writing it up. So it's in principle, we maybe expect some changes, but we are growing. Like there's an increasing level of confidence that everything will work out as described in this diagram. All right, so that's the teaser. And the point here is that this construction works in dimensions higher than 1 because
please, can you explain where, after forgetting our manifold X, where Riemann metric are defined? In manifolds which are included in category of bordism, yes?
So there are two Riemannian metrics in the game here. One metric is a Riemannian metric on X. X is a Riemannian manifold.
Yes.
And the other Riemannian metric is a Riemannian metric on the bordisms. And these two metrics are different metrics. So they are both present in this picture. So in this category, a bordism is a one-dimensional Riemannian manifold that maps into another Riemannian manifold X.
Okay, I understand.
Yeah. Yeah, and just as a little remark, what enables this construction is a geometric cobordism hypothesis. So the geometric cobordism hypothesis allows you to compute the space of Functorial field series of dimension d, in our case that's just 1, with geometric structure S. In our case, this will be either a Riemannian metric or a Riemannian metric together with a map to X. And the category of values V, in our case, is just vector spaces. It allows you, so the category of such symmetric monoidal functors can be computed as a certain very simple mapping space from S into something called the space of fluidizable objects and their invertible morphisms. And let me not explain the meaning of the details here, but just give you a very rough idea of why this, for example, allows you to do the quantization construction. Okay, here, yeah, I really need to rescale. Oops. Yes, why this enables you to do the quantization construction. So you have a classical field theory P, which lives in this space of one-dimensional Functorial field series, where bordisms are equipped with a Riemannian metric and a smooth map to X with values in vector spaces. And you want to produce a quantum field theory Q, which is also a one-dimensional Functorial field theory, where bordisms are now equipped just with a Riemannian metric. And this field theory takes values in vector spaces. And yeah, on this, so to produce Q from P, we want to define a push-forward map like this here, which in principle has to be defined using those infinite dimensional path integrals, which are very difficult to define and manipulate. The geometric cobordism hypothesis allows you to, however, to replace the true objects, the true spaces of Functorial field series on the left, with much easier spaces on the right. This will be just maps, or if you prefer, natural operations from Riemannian metrics times X to the space of vector spaces and invertible maps, and likewise here. And very roughly speaking, you should think of those, very roughly speaking, as maps between finite dimensional smooth manifolds. That's not quite true. It's not really that. It's not at all true, but it's roughly speaking, that's how you should think about this. So on this side, the right side, you are given some map of something that looks and behaves roughly like finite dimensional smooth manifolds. And you want to produce another map of finite dimensional smooth manifolds. And you now see your problem is all of a sudden finite dimensional. So again, this is not literally true, but roughly speaking, the point is like everything is finite dimensional here. The infinite dimensional integrals that we previously had to define no longer have to be defined because the geometric cobordism hypothesis took care of this for us in a sense, because well, the point is that a Functorial field theory has a lot of structure in it, and the geometric cobordism hypothesis exploits the structure to drastically simplify the description of your Functorial field theory, which eventually allows you to get rid of all those infinite dimensional integrals.
So stupid question. So when you want to define the infinite dimensional path integral, so what you do is you go from the upper, so you just invert this one arrow by means of a weak inverse, something like this, and then take the contribution. Okay, I see. Thanks.
Yeah, precisely. Yes. Yes. Yeah. So in a sense, yeah. I mean, it's yeah. I mean, the inverting the bottom arrow, so to say, roughly speaking, amounts to basically taking the exponent of the Hamiltonian. So here, this bottom right corner will more or less encode your Hamiltonian H, which is in our case is simply the Dirac operator, maybe squared, and inverting the bottom map roughly amounts to taking the exponent of the Hamiltonian. Yeah. And of course, like as I mentioned, this is just a very, very rough picture, and unfortunately, for you, and it's there's a lot of formalism present here. Like, and let me just very briefly mention what has been left out because I'm already running out of time. Yeah, it's a good question. How long do we want these lectures to last? Like I can go for many hours, but I don't think I should go for more than an hour and a half, I would say, because probably it's difficult. Already like 20 minutes over time. So probably we should stick to like an hour and a half at best, I bet. Unless there are different opinions, of course. But
Or we can have 2 hours with a break in the middle, but
yeah, we should probably have had a break. Yeah. But for now, we are on the last page. So let me just give you a very brief overview what will happen in the forthcoming lectures. So we have to define all those gadgets that I may have mentioned. So like something like a smooth symmetric monoidal infinity D category. That's a very sophisticated gadget, which, I mean, all those words would have to be defined. Each of those words carries considerable abstraction behind it, especially like infinity D categories. Then we have to define the category of Bordisms as such an object. And this again incorporates the work of many, many people. And again, it occupies pages and pages of definitions. It's not a definition you can write down in a single paragraph. And only after that we will be able to state the geometric Bordism hypothesis. So already for part A, even to define what a smooth symmetric monoidal infinity D category is, we need tons of prerequisites. We need a lot of, like, all of higher category series treated using homotopy theory. And homotopy theory requires, at the very least, simplicial sets, model categories, homotopy colimits, various constructions like Siegel's gamma objects and complete Siegel spaces, simplicial presheaves, and descent for simplicial presheaves. At some point, we'll need at least diffeological spaces. Unfortunately, all of that is not added here for the sake of generality. It's rather forced on us by specific examples we want to encode from physics. For example, like smooth, we need smooth, and therefore the formalism of simplicial presheaves and diffeological spaces, because we do want, it's absolutely essential we have smoothness, because this will allow us to classify functorial field series. The infinity D business is necessary because we want to encode geometric structures like gauge fields, or if you prefer, principal bundles with connection. And more sophisticated ones like the B field, the C field in supergravity, the Ramon field, which do requires the full power of homotopy theory. So it's let me stress for you that I'm not trying to define something the most general thing for you possible, but rather I'm only trying to define for you what is a minimally necessary structure to perhaps be able to talk about examples that we ultimately want to do in physics, like quantum mechanics and conformal field theory, and maybe at some point even Young-Mills theory and similar physical constructions. Yeah, so we'll need to study all this homotopy theory, and this will be a lot of homotopy theory, so this will take months to explain. And only after that, I will be able to properly talk about higher category theory. Only after that, I will be able to talk about geometric structures and Bordism categories, or more precisely, higher categories of Bordisms. And this is what finally will enable us to talk about examples. Yeah, so unfortunately, as you can see, there is quite a bit of material ahead of us, so it's not like we are going to jump right in and start computing specific examples. We'll need to talk quite a bit about the machinery. But I do plan to start very elementary, so we'll start by explaining what simplicial sets are, what model categories are, how to work with homotopy colimits, how to work with gamma objects, and so on and so on and so on. So in principle, if you don't have any background, you should be able to see what you have to study. Okay, I think that's it for today. That's it for today. Just to return back to what I mentioned at the very beginning, if you're interested in the optional activities, please maybe stay in the room. We can discuss how to organize this. But otherwise, that's it for today. And thank you for your time. And I hope I see you next time.
I have two further questions, if that's fine.
Yeah, of course. Go ahead.
So first of all, is it probably possible for the next few times that you put up the lecture notes beforehand so that we can...
Yes, absolutely, yes. In fact, I think I wanted to do this before this one, but I forgot to do it. Yeah, I will try to put them online before the talk starts. Yeah.
And then also, how long do you think this course will...
Sorry. Yeah.
How long do you think this course will go? So will it? You said several months. So is it open-ended?
It's a good question. It's I guess, and it will go as long as there are at least 5 people in the room, I guess, or so. Or at least 4 people, I would say, because if there are fewer than 4 people, I'm not sure if there's enough audience to continue. But in principle, we can go as long as we want to. Certainly until the end of December. But for now, the schedule with Sundays will stay until the end of semester, which is December 5th. So the semester ends on December 5th. So after December 5th, we can pick a different day if we want to. We don't have to, but we can pick a different day. So in principle, it's open-ended, more or less. I mean, we can go as far as we want to, or at least until we establish our goals, which is to construct maybe some examples of functorial field series. Yeah.
Okay, thank you.
You're welcome.
Will we go over the field theories are local proof from your first paper, like in some detail?